Today we are looking at truth tables. This is a new and important terminology. So they are integral to solving circuit problems and can be challenging based on the Boolean expression provided. So I'm writing here that they are used for everything. Yes, they are the heartbeat for schematics, for layouts, for finding the least number of transistors. Something to remember is that if there are n inputs, there are 2 to the power of n possible expressions or combinations for that Boolean expression. And that is shown on the rows of the truth table. The rows extend from top to bottom, and the outputs can have subfunctions within, making the solving easier. Here I'm writing an example that I find easier to comprehend, may not work for everyone. Looking at possible plotted points on a graph, once we find the pattern of the curve, we get the equation of the line. This is something that is studied in grade school. The same way from the ones and zeros we obtain from this Boolean function, we find the pattern of the expression. If this didn't help, please disregard it. So now we're going to go into our first example. First, I'm going to detect how many inputs there are. There are 4 inputs, meaning that there is 2 to the 4th, or 16 combinations. So I've written out the 16 combinations, but I'm going to explain how I did that. The inputs grow more significant from right to left. So for the least significant bit, which is D, the zeros and ones pattern repeat every 2 rows. For the input C, the cycle repeats every 4 rows, with the zeros and ones equally spaced with each cycle. For B, the cycle repeats every 8 rows. For A, which is the most significant bit, MSB, it repeats every 16 rows. So we have exhausted all possible combinations. We can now use the truth table to our advantage by creating helpful subfunctions. If we were to apply the truth table with solving mainly for f, it would be very long and tedious. So to help with evaluation, having subfunctions makes the deduction efficient. First, we are looking at the term x1, which is not A or B or not C. One approach is to go through each row and fill out the values for x1. So say A is 1, and we have not A. That means not 1 is 0. So that's not very useful. Say A is 0. Not 0 is 1. So that means x1 will be 1 for the rows that A is 0, because this is an OR subfunction. So this means that row 0 is 1, row 1 is 1, row 2 is 1. And it is also important to make sure you fill out the structure in your columns so that you don't accidentally make a mistake. So I'm writing in my lines to make sure I didn't. confuse anything. You can try pausing and seeing if you can complete the first half of the table. So row 8, we've reached a point where a is no longer 0, and I'm realizing that all 3 variables are now going to trigger a 0. Why is that? Because a is 1, b is 0, and c is 1. So that means for the next 2 functions, when it says 1, 0, 1x, those 2 will be 0. I am now creating the second subfunction, which is y1 equals not a or not b or d. So the first approach was slow, but there is a second approach. It uses the concept of De Morgan's law. So we ask the question, when is y1 0? It's when a is 1 and b is 1 and d is 0. And we don't care about input c's values. So where will we find these? I find an occurrence at row 14. So I'm filling that out as a 0. There's another occurrence on row 12. Because it doesn't repeat anymore, everything else would be classified as a 1 for y1. Filling out the rest of the table labels quickly. So Z1 and F. Z1, W1, and F. W1 is the 4th term, Z1 is the 3rd term. So now we're trying to find out when is Z1 0. So that would be when B is 0 and C is 0 and D is 1. We don't care about A. And don't care is written as X usually. So we find those values in the table, in the input column, and those are the ones that are written as 0. Everything else is written as a 1. So W1, when is W1 0? That is when A is 0 and B is 0 and C is 0 and D is 0. I say and because all need to be 0 at the same time. If one of them is not a 0, W1 is a 1. So that means row 0 is the only place where there will be a 0 for the whole rest of the column. So right now I'm filling out the lines of the table so that it is more legible for future computation. Aligning the correct subfunctions together will verify my and reduce the percent error for when I compute the final output. And the last part is when F is an AND gate. So for the AND gate to happen, X1, Y1, Z1, and W1 all need to be 1. So that means for any place that we see 0, we can write F in as 0. That's the end of the video. Thank you.